In 1930, a 22-year-old Royal Air Force officer filed a patent for an engine that would change the world. No propeller, no pistons, just air, fuel, and thrust. 500 miles an hour when the fastest planes on Earth could barely reach 150. The British government looked at it and said no. Industry said impossible. And then the patent expired because Frank Whittle could not afford the renewal fees on a serving officer's pay. Every technical detail became public. It reached Germany 9 years later. A German jet took off from the Baltic coast. 4 days after that, the Second World War began. By the time Britain's own jet finally flew, it was faster than the Spitfire. But the car company hired to build its engines delayed the fighter by 2 full years. And the genius engineer who invented it all was working himself to collapse, fighting not the enemy but his own country. This is his story. The city of Coventry in 1107 was smoke and iron. Factories built machine tools, bicycles, motorcycles, and the first generation of British automobiles. The noise of industry was the background music of daily life, and for the families who lived in its shadow, engineering was not a profession. It was just what your hands did. Frank Whittle was born there on the 1st of June. His father, Moses Whittle, was a foreman at a machine tool manufacturer, a man who understood lathes and pistons and the weight of metal the way a farmer understands soil. When Frank was 9, the family moved to Leamington Spa, a quieter town 20 minutes south, because Moses scraped together enough money to buy a business. It was called the Leamington Valve and Piston Ring Company. The name was grander than the reality. It was a tiny workshop, almost nothing, but for a boy, it was everything. Frank worked in his father's shop from the beginning, cutting slots in valve stems, watching lathes spin, learning the feel of metal under a file, the sound a bearing makes when it is seated right, the way a piston ring must be gapped to the 1,000th of an inch, or it will fail. Moses paid him 2p an hour. It was not charity. The boy was useful. This was where the hands of a genius engineer were made. Not at a university, not in a laboratory. In a cramped workshop in a market town, for 2 pennies an hour under the eye of a father who expected precision because precision was the only thing that kept his business alive. But the hands were only half the story. Leamington Spa had a public library. Frank Whittle went there the way other boys went to the cinema. He was lazy with homework, his teachers said so, and he never won a single prize at school. But at the end of each term, he would come top in mathematics, as if the effort of daily study bored him. But the challenge of a final exam woke something up. The library was where the real education happened. He read outside the school curriculum, aerodynamics, thermodynamics, and for the first time, in a book he pulled from a shelf meant for adults, he read about gas turbines. He was 13 years old, and he was already in love with flying. Since the age of 4, his favorite toy had been a tin model of a Blériot monoplane 1911, the year the toy was made. His heroes were not footballers or boxers. They were Captain Albert Ball and Major James McCudden, the Victoria Cross pilots of the First World War. Men who climbed into canvas and wire machines and did not always come back down. Frank Whittle wanted to fly, and in 1923, at the age of 15, he found a way to try. The Royal Air Force was recruiting apprentices. Whittle applied. He went to the selection camp, passed every written test, and was rejected. He was too small. The numbers were final. Too short, too light, not enough chest. The Royal Air Force had physical standards, and a boy from a valve workshop in Leamington Spa was sent home. This is where most stories would end. A boy is told no. The door closes. He finds another path, a factory, a trade, a smaller life. The world is full of doors that close on 15-year-olds who are built the wrong way. But something happened at that camp that the bureaucracy did not plan for. A physical training sergeant, a man whose name has not survived in any record, took pity on the boy. He could see something in Whittle. Desire, intelligence, the particular stubbornness of a person who does not accept that the world is fixed. The sergeant gave him a diet, a set of exercises, Max Alding exercises, a system of muscle control popular in that era. He told the boy to go home and follow the program. Frank Whittle followed it for 6 months. He gained 3 inches in height, 3 inches around his chest. And then he did something that tells you everything about the man he would become. He wrote to the Air Ministry and asked it to reapply. They said no. The rule was absolute. Once rejected, always. No exceptions, no appeals, no second chances. Whittle applied again anyway, as if he had never applied before. A clean application. A new name on a new form. He was betting that the bureaucracy was too large and too disorganized to notice that the same boy was walking through the same door twice. He was right. Nobody caught it. The paperwork sailed through, and Frank Whittle, rejected, too small, told never to come back, arrived at RAF Cranwell as an apprentice in No. 4 Wing. He had beaten the system for the first time. It would not be the last. But it set a pattern that would define his entire life. The system says no, and the genius finds a way around it. Not through connections, not through wealth, through sheer, calculated, stubborn nerve. Life as an apprentice was not what Whittle wanted. In that rank, he would never fly. The apprentices maintained aircraft. They cleaned them, repaired them, watched other men take off and land. For a boy who had dreamed of the sky since he was 4, it was a kind of slow suffocation. What saved him was the Model Aircraft Society, the Boys' Wing Model Aircraft Society WWII. Whittle became its leading figure, building working replicas with a precision that startled everyone around him. The joke on the base was that BWMAS actually stood for Boy Whittle's Model Aircraft Society, because every design that mattered came from his bench. The models were small, the ambition behind them was not. Whittle was thinking about flight, the way an engineer thinks, not just how to get into the air, but how to stay there longer, go there faster, climb there higher. His model aircraft were not toys, they were experiments, and they were noticed. When the time came to select 5 cadets from No. 4 Wing for officer training, the most exclusive path in the entire RAF, Whittle's name was on the list. Barely. He was 6th. The top 5 would go forward to the officers' training college, and the 6th would stay behind. Then the No. 1 boy failed his eyesight test. Frank Whittle was in. Even then, the system nearly stopped him. Lord Trenchard, the founder of the Royal Air Force, a man whose word was close to law, almost blocked the promotion. Whittle had not been a leading boy. He had no record in sports, and sports mattered enormously in a military culture modeled on the English public schools. But Whittle's commanding officer fought for him, and fought with a single argument that Trenchard could not easily dismiss. He said he believed he had a mathematical genius. Less than 1% of RAF apprentices ever made the leap to officer cadet. Whittle made it not because the system wanted him, but because one man saw what nobody else could see and said it out loud at the right moment. Cranwell changed everything. The officers' training college sat next to the apprentices' wing, but socially it was another world, a world of public school manners and inherited confidence, where most cadets arrived already knowing the rules of a class that Whittle had never belonged to. He was a factory foreman's son among the sons of gentlemen, but Cranwell taught him to fly. The aircraft was the Avro 504K, an ancient biplane designed before the Great War, with a wooden skid between the wheels that was meant to stop it tipping forward on its nose. In practice, Whittle said, it helped the plane tip over, or even turn upside down. He was a natural, fast reflexes, an instinct for the machine, and a confidence that crossed the line into recklessness more often than his instructors liked. He would later confess, almost cheerfully, that he wrecked at least 3 aircraft. The first time, he got lost in bad weather and forced a landing on the same day as the Cranwell cross-country runner race, Every cadet hated. His fellow cadets were convinced he had crashed the plane on purpose to avoid the run. He was daring. He was brilliant. And in between learning to fly and destroying the occasional airplane, he was thinking. All cadets at Cranwell were required to write a thesis. Most chose safe topics. Whittle chose one that was, by his own admission, rather ambitious. Future developments in aircraft design. He wrote it during the first half of 1928, drawing on 5 years of training and a lifetime of private study that had begun in the Leamington Spa Library. The thesis was dense with mathematics. It derived independently from first principles. What Whittle later learned was the well-known Breguet range equation, connecting speed, range, altitude, and engine efficiency. He had never seen the formula. He had arrived at it on his own, and his conclusion was devastating. If you wanted to fly very fast and very far, you had to fly very high. 50,000 feet. At those altitudes, the air was too thin for a piston engine. The engine would lose power fighting its own internal friction, and at speeds above a certain threshold, the propeller itself would fail, the tips approaching the speed of sound, the drag becoming impossible. Every airplane in the world was approaching a wall. The piston engine and the propeller had a ceiling and a speed limit built into the laws of physics. No amount of engineering could overcome it. The technology was dying. Whittle proposed the alternative. Remove the piston engine entirely. Replace it with a turbine. Use the force of expanding hot gas, the same principle that makes a released balloon shoot across a room, as the thrust itself, 500 miles per hour. When the fastest aircraft in existence barely reached 150, his professor read the thesis, wrote on the cover that he did not, in effect, really understand it, and gave it 30 out of 30. This was the mark of Whittle's genius. Not the idea alone. Other engineers had thought about gas turbines, but none of them had seen the full picture the way Whittle saw it. The altitude where piston engines failed was exactly the altitude where a jet engine thrived. The cold, thin air actually benefited the compressor. The exhaust velocity that would date in a conventional engine was, in a jet, the entire point. Every disadvantage of flying high and fast became, in Whittle's design, an advantage. After the idea came to him, he said, he thought, my goodness, why didn't I think of this before? It seemed so obvious then. That is the signature of genuine breakthrough. The solution, once found, photo, looks inevitable, but nobody else found it. He was 21 years old. By the summer of 1930, Whittle was 23. Now he had left Cranwell and was stationed at the Central Flying School at Wittering, training as a flying instructor. There he met W.E.P. Johnson. Pat Johnson, another instructor, who happened to have trained as a patent agent. Johnson listened to Whittle's idea, studied the mathematics, and told him it would work. Together, they drafted a patent for the turbojet engine. It was filed on the 16th of January, 1930. Frank Whittle, pilot officer, age 22, son of a valve maker from Leamington Spa, had just filed the blueprint for the future of powered flight. Armed with his patent, he took the idea to British industry. Company after company turned him down. The theoretical problems were too large, they said. Compressors were too inefficient. Turbines were too inefficient. The materials available in 1929 could not withstand temperatures above 500 degrees centigrade. Whittle believed those materials would improve. He was right. But nobody else believed it yet. He went to London, to the Air Ministry itself. He was taken to see A. Griffith, one of the ministry's senior scientists, a man who was pursuing his own research into axial compressor design. Whittle explained his turbojet concept. Griffith pointed out an error in the calculations. The meeting was cold. The reception was, in Whittle's words, very cool. Then the letter came. The Air Ministry was not interested. It did not help, Whittle noted. that he had not yet received an engineering degree, a pilot officer with a patent and a thesis score of 30 out of 30 but no formal qualification. In the eyes of the establishment, he was not a scientist. He was a junior officer with an ambitious idea. He was nearly posted to No. 4 Flying Training School at WWII, Egypt. If that had happened, its words, it would have been a real nail in the coffin of the jet engine. An inventor buried in the desert, thousands of miles from any workshop, any laboratory, any chance of building what he had designed. The posting was changed at the last moment. Whittle stayed in Britain. In May of 1930, he married Dorothy Lee. It was a brief season of happiness. Whittle was selected for the Hendon Air Pageants, the public air shows, where the RF's best pilots performed aerobatics for enormous crowds. Crazy flying, they called it. Loops and rolls and dives that pushed the aircraft to its limits and the audience to its feet. The red arrows of their day. Whittle loved it. For a few months, the genius engineer was simply a pilot free, admired, doing the thing he had dreamed of since he was 4 years old, with a tin Blériot in his hands. It would not last. In 1935, his patent expired. The renewal fees were more than Whittle could afford on a serving officer's pay, supporting a wife and 2 young sons. The patent lapsed. Every technical detail, every diagram, every specification that Frank Whittle had conceived became public record, available to anyone. The patent was now freely accessible. Whether it was read in German aviation circles, and by whom, remains one of the unanswered questions of this story. What is certain is that Frank Whittle's idea was no longer protected. At the exact moment that Hitler was rebuilding the Luftwaffe from nothing into the most formidable air force in Europe, the genius engineer had invented the future. His own government had refused it, and now that future belonged to anyone who cared to read the published specifications. In September of 1934, the Royal Air Force made a decision about Frank Whittle's future. They did not ask him. They simply told him. Every general duties officer, after force service, was required to specialize. Most were given a choice: engineering, radio, navigation, physical training. Whittle was not given a choice. He had spent years pestering the Air Ministry with inventions and proposals and ideas they did not want to hear. So they looked at this troublesome young officer and said, "You will be an engineer, and you will go to Cambridge." It was meant as a way to channel his restless mind into something useful. What it actually did was arm him. Cambridge in the 1930s was one of the finest scientific institutions on Earth. Whittle entered Peterhouse to read the Mechanical Sciences Tripos, the most rigorous engineering degree the university offered. And for the first time in his life, he had access to the full depth of thermodynamic theory, materials science, and compressor research that his public library education had only sketched. The knowledge cut both ways. On one hand, he could now see that his turbojet concept was sound, the physics held, the mathematics worked, the principle was right. On the other hand, he became more aware of the difficulties. The gap between a valid concept and a working engine was enormous. Compressor efficiency, turbine blade metallurgy, combustion stability at pressures no one had ever attempted. The problems were real, and Cambridge made them sharper. He might have stayed in that state, but unable to act for the rest of his career. Then a letter arrived. It came from Rolf Dudley Williams. They had known each other at Cranwell, 2 young officers who shared the particular energy of men who believed the RAF could be more than it was. Dudley Williams had left the service, but he had not forgotten Whittle's idea. He had been talking about it to businessmen, to contacts, to anyone who would listen. And someone had listened. The letter was brief, a hurried note. Dudley Williams had met a man who was, in his words, a bit of a big noise in an engineering concern. This man was interested in the turbojet. Very interested. Whittle kept the letter for the rest of his life. On the top of it, in his own handwriting, he wrote a note that said, This letter changed the course of my life and triggered a revolution in aviation. Dudley Williams came to Cambridge with another former officer, J.C.B. Tinling. The two men sat down with Whittle and proposed something that the Air Ministry had never offered, that British industry had never considered, and that no one in government had thought worthwhile. They proposed to form a company, to raise private money, and to build the jet engine. The mechanism was a merchant bank. Falk and Partners were approached by an intermediary, an engineer named Bramson, a man with genuine credentials in aeronautical engineering. Williams and Tinling had found him. Bramson examined Whittle's work, wrote a comprehensive technical report, and delivered a verdict that was wholly favorable. Falk and Partners read the report and agreed to back the venture. In March of 1936, the company was registered. Power Jets Limited. Whittle told his new backers plainly and without false hope that the project had a 1 in 30 chance of success. They accepted those odds. It tells you something about the force of Whittle's conviction, that he could look a room of bankers in the eye, say the word 1 in 30, and walk out with their money. The Air Ministry responded with a leash. An official from the ministry named Toll informed Whittle that he was not to work more than 6 hours per week on the project. 6 hours. For a man redesigning the future of powered flight, Whittle ignored the order completely. He worked on the engine nearly full-time nights, weekends, every stolen hour he could find. And at the same time, he was preparing for his Cambridge finals. He wanted a first-class honours degree. Not because it would help the jet engine, because he wanted to prove to himself, to Griffith, to the ministry that had dismissed him, that the man they had rejected was not just an inventor with an interesting idea. He was a first-class engineer by any standard they cared to name. He got the first, and then he turned back to the engine. This is what genius looks like when it is not celebrated, not recognized, not supported. It looks like a man working 2 impossible jobs at once, designing a revolutionary engine while passing the hardest engineering exam in the country in violation of a direct order from his own Air Ministry, funded by a merchant bank that gave him almost nothing, with a 1 in 30 chance of success. And he did both. The next problem was building the thing. Whittle drove from Cambridge to the city of Rugby, to the works of British Thomson Houston. BTH was a large company. They built steam turbines. They had the machine tools, the metallurgical knowledge, and the manufacturing capability to construct a jet engine if anyone could. Whittle rehearsed what he would say. He had to persuade this enormous company to accept a contract for a project that most of the scientific establishment considered impossible, and the fee he could offer was £2,000. 2,000. The proper way to develop a jet engine: build a compressor and test it separately. Build a turbine and test it separately. Build combustion chambers and test them separately. Then assemble the whole would have cost 30,000, 15 times what Whittle had. There was no hope of getting that kind of money. None. So Whittle proposed the only alternative: skip the component testing. Build the complete engine from the start. Prove it right from the word go. It was a gamble that no responsible engineer would recommend. But responsible engineering required £30,000, and Frank Whittle had two. BTH accepted. In a cavernous workshop in Rugby, the world's first jet engine began to take shape. Whittle stood over it, day after day, watching every component being machined, checking every tolerance, arguing every specification. He was confident about the centrifugal compressor. The mathematics were solid, the design was clean. He was reasonably confident about the turbine, but the combustion chamber worried him. The problem was intensity. The jet engine required combustion at 24 times the intensity of any existing system. 24 times. No one had ever sustained a flame at that pressure, at that temperature, in that volume, for any length of time. The materials of 1937 were not designed for it. The engineering handbooks offered no guidance because no one had tried. On April the 12th, 1937, The engine was ready for its first proper test run. Many people had said it would not even tip itself over, that it would sit on the test stand like an expensive piece of sculpture and do nothing. The skeptics had good theoretical reasons on their side: inefficient compressors, inadequate materials, combustion instabilities that would snuff the flame before the turbine could spin. What happened proved the very opposite. Whittle gave the signal with his hand. Raise the speed to 2,000 RPM. The electric starter motor spun up. Whittle opened the main fuel control. The engine started, and it kept going. It accelerated beyond the control setting, beyond any safe limit, beyond anything the instruments were designed to measure. A pool of fuel had accumulated in the combustion chamber. Nobody knew it was there, and it was feeding the turbine independently of the fuel valve. The engine was running on its own. It sounded like perpetual motion. Every man in the building ran. Down the factory floor, out the doors, into the open air. Grown engineers, experienced mechanics, men who had spent their careers around machinery, they ran, because the sound was unlike anything they had ever heard. And the machine appeared to be beyond all human control. Whittle did not run. He stood 3 feet from the engine, frozen, not brave, paralyzed. In his own words, petrified with fright. The fuel burned off. The engine slowed. The scream died. It happened 4 more times in the days that followed. 4 runaways. 4 moments when the machine seemed to have a will of its own, and every sane person in the room chose distance over curiosity. But the principle had been proven. The turbojet worked. Air went in, was compressed, was mixed with fuel, was ignited, expanded through the turbine, and came out the back as thrust. It worked. Frank Whittle had been right since 1928. And now there was a machine in a rugby factory that proved it. He submitted a report to the Air Ministry. It was reviewed by A. Griffith, the same Griffith who had dismissed Whittle's idea in 1929. The same man who had pointed out the calculation error. The same scientist who was pursuing his own compressor research and who had every professional reason to see Whittle fail. Griffith's report damned the engine with faint praise. He listed every difficulty. He noted that without a propeller, the aircraft would lack the slipstream needed for takeoff. He emphasized the inadequacy of the materials. He acknowledged that the engine had run but framed it as a curiosity rather than a breakthrough. The genius had built the machine. The system had looked at it and shrugged. And while Frank Whittle fought for every pound and every hour in a factory in Rugby, 1,200 miles to the east, a very different story was unfolding. Hans von Ohain was born in 1911, 4 years after Whittle, in a Germany that was rebuilding itself first from the devastation of the Great War, then under the ambitions of the Third Reich. He studied physics at the University of Göttingen, one of the finest scientific institutions in Europe, a place where the walls themselves seemed to vibrate with a legacy of Gauss and Riemann and Born. Von Ohain's path to the jet engine began not with mathematics, but with disappointment. His first flight was on a commercial airplane, a 3-engine Junkers. He had dreamed about it for years, the beauty of flying, the elegance of being above the earth. And then he climbed aboard, and the reality hit him. The noise was enormous. The vibration rattled his teeth. The smoke from the exhaust streamed past the windows like a factory chimney laid on its side. He felt, he said later, that the piston engine and propeller destroyed the elegance of flying. This was a different starting point from Whittle's. Whittle had been driven by speed and altitude, the performance limits of the piston engine, the mathematical certainty that it would fail at the extremes. Von Ohain was driven by aesthetics. He wanted smooth flight, quiet flight, flight that felt the way flying was supposed to feel. But as he thought about it, he arrived at the same destination: a turbine engine, a jet, no pistons, no reciprocating parts, just the continuous flow of compressed air, fuel, and expanding gas. And he noticed, as Whittle had noticed years before, that such an engine would not only be smoother, it would also be faster. Von O'Hain was brilliant, but brilliance alone did not explain what happened next. What explained it was a name, Ernst Heinkel. Heinkel was a legend in German aviation. He had built some of the fastest aircraft in the world. He was obsessed with speed, obsessed in the way that only a man who has spent his entire life pushing machines to their limits can be. When von O'Hain was introduced to him, Heinkel did not hesitate. He invited the young physicist to his private villa in Warnemünde, on the Baltic coast. Von O'Hain arrived alone. Heinkel listened to his ideas, and then he made an offer that Frank Whittle would never receive from anyone in Britain. He said he would finance the entire project himself, out of his own pocket, with his own company, his best aerodynamicists, his best designers, his best engineers, everything von O'Hain needed, immediately, without committee, without approval, without a single form to fill out. Von O'Hain looked at the Baltic Sea through the villa windows and thought this would be a nice place to work. He also thought something else. He had been afraid to approach the large engine companies' firms like BMW and Junkers Motoren because he felt they were too ingrained in their piston engines, too set in their ways, too likely to dismiss a young physicist with an unproven concept. Heinkel was different. Heinkel wanted the future. And there was one more thing. When von O'Hain was asked, years later, about the financial side of the development, he said something that lands like a hammer when you set it next to Whittle's story. Money was not a problem. 4 words, an entire world of difference. While von O'Hain worked in a fully equipped factory on the Baltic coast with the best engineers in Germany and unlimited funding from one of the most powerful men in German aviation, Frank Whittle worked in a rented space in Rugby with a team he could count on one hand, reusing damaged parts because he could not afford new ones, hiding from an air ministry that had told him to limit his work to 6 hours a week. 2 geniuses, the same idea, 2 utterly different systems, and the system with the money was going to win the race. On August the 27th, 1939, 4 days before Germany invaded Poland, 4 days before the Second World War began, test pilot Erich Warsitz climbed into the cockpit of the Heinkel He-178 at an airfield near Rostock. The engine had been tested on the ground. A few hours at the very most. Von O'Hain was certain it would work, but certainty and proof are not the same thing, and proof requires a man willing to strap himself to an untested machine and leave the ground. Warsitz started the engine. The He-178 rolled down the runway, and then it lifted off. It flew. Warsitz disappeared from sight. The team on the ground waited and waited. Then he came back into view, and instead of landing, he went around again. Another circuit. He was enjoying it. He landed and stopped the aircraft just behind where Heinkel stood. He climbed out and said everything functioned beautifully. The engine worked well. He was genuinely enthusiastic. They had a nice festival. That evening, a jubilant Ernst Heinkel picked up the telephone and called General Ernst Udet at the German Air Ministry. Udet, a legendary World War I ace, now one of the most powerful men in the Luftwaffe, listened to Heinkel's breathless announcement. Then he replied, "Congratulations, but let me sleep. It's an ungodly hour." The first jet aircraft in history had just flown, and the man responsible for German air power wanted to go back to bed. Frank Whittle knew nothing about any of this. In the autumn of 1939, as war broke out, power jets was dying. The financial backers were getting cold feet. They had invested with the expectation, quite unrealistically. Whittle said that within a few months, the company would have an engine capable of flying in the stratosphere. Instead, they got breakdown after breakdown, component failures, combustion instabilities, turbine blades that cracked and warped under temperatures they were never designed to endure. The investors lost heart. They did not produce the money they had promised. The Air Ministry's response was grudging and conditional. After the engine's first run had proven it could at least sustain itself, they agreed to a very limited contract. But this contract came with a chain. The moment the ministry gave Power Jets government money, the project fell under the Official Secrets Act. Whittle could no longer tell anyone what he was working on. He could not approach new investors. He could not explain his technology to potential partners. He could not walk into a boardroom and say, "I have a revolutionary engine. Here is what it does. Here is why you should fund it." The conversation was now illegal. "You cannot go to someone," he said later, "and say, 'Look, we have a damn good idea. Would you let us have some money? We can't tell you what it is, but it's very good.' No, it couldn't be done. By 1939, the total amount Britain had spent on the jet engine, on the single most important propulsion technology, since the internal combustion engine, was £7,000. And on the last day of June that year, Frank Whittle was scheduled to leave Power Jets. His RAF assignment to the company was ending. The system was about to pull him out. On that final day, June the 30th, 1939, an important visitor came to see the engine run. His name was David Pye. He was the Director of Scientific Research at the Air Ministry. This was the highest-ranking technical official who had ever paid attention to Whittle's work. Whittle needed the engine to perform. Not for 20 seconds, not for a minute. He needed it to run long enough to convince a man who had the power to save the entire program. The engine ran for 20 minutes. Pye watched it, the steady roar, the heat shiver off the exhaust, the instruments holding steady. 20 minutes of a machine that half the scientific establishment said could not work, running as smoothly as a turbine in a power station. David Pye became a complete convert. On the drive back to the railway station, Whittle was behind the wheel. Pye spent the entire journey explaining to Whittle the advantages of his own engine. It could run on any fuel, it was vibrationless, it was mechanically simpler than any piston engine ever built. The future was obvious. Whittle sat quietly and drove. He was a squadron leader. Pye was the director of scientific research. The inventor listened politely while the bureaucrat explained his own invention to him. "I thought," Whittle said later, "you're telling me." Pye agreed that an engine for flight should be ordered, and an airplane to use it. This was the turning point. The turbojet was saved for Great Britain, not by the system working as it should, but by 20 minutes of a running engine on the last possible day, witnessed by the one man who happened to have the authority to say yes. If Pye had not come that day, if the engine had failed that day, if Whittle's posting had ended 1 week earlier, the jet engine would have died in Britain, and the story you are listening to would be a German story, told in a very different way. Power Jets moved. The workshop in Rugby was too small, too public, too exposed. Whittle found a new home for his work, the Ladywood Works in Lutterworth, a town in Leicestershire. It was a disused foundry. There is nothing there today to show that history was once made inside its walls. But in 1940 and 1941, this was where Britain built its answer to the Luftwaffe's jets. Whittle himself worked at Brownsover Hall, a country house nearby. He worked through the night. Every night, he understood with a clarity that the ministry did not share that his work could shorten the war, that every month of delay was measured in lives. He drove himself beyond exhaustion, swallowing benzodrine tablets to stay awake, pushing through on nerves and willpower. And the knowledge that across the Channel, Germany was not waiting. His son David remembered him in those years, a man who was always working, always. If he took a Sunday off, he sat by the fire with a slide rule and scraps of paper spread across every surface. A little bit of time for the boys. But not much, not much. Dorothy knew something important was happening, but not what. The Official Secrets Act meant that the man who came home at midnight and woke at 4 could not tell his own wife why. She used to say, "Oh, well, Daddy is doing something very hush, hush." The team at Lutterworth grew. Whittle recruited with the same intensity he applied to engineering. First-class honours from Cambridge. First-class honours from Oxford. Imperial College of Science. He wanted the best minds in Britain, and he got them, though the recruitment process was absurd. The advertisements could not say what the job was. The interviews could not explain what the candidates would be working on. Some of them guessed, Whittle thought, from the questions he asked. By May of 1941, the engine was ready to fly. The aircraft was the Gloucester E-2839, an experimental plane designed by the Gloucester Aircraft Company specifically to test Whittle's turbojet. Small, sleek, with a single engine mounted in the fuselage, and no propeller, it looked unlike anything the Royal Air Force had ever built. For its maiden flight, the aircraft was taken to Cranwell, the same Cranwell where Whittle had arrived as an apprentice 18 years earlier. The same Cranwell where he had written the thesis that scored 30 out of 30. The same Cranwell where a commanding officer had saved his career by telling Lord Trenchard he had a mathematical genius. On May the 15th, the weather was uncertain. Whittle drove to Lutterworth in the morning, thinking the flight would be postponed. Then a message came the weather was clearing. He rushed back to Cranwell. That same day, a young naval pilot named Eric Brown had been forced to land at the base. Brown was not part of the jet program. He knew nothing about it. He was on a routine flight and needed to stop for weather. When he landed, he was surprised to find the base full of civilians, an unusual number of people, an unusual atmosphere. When he went to check in at the officers' mess, he asked what was going on. Nobody would give him a straight answer. There was, he said, almost an air of conspiracy about the whole place. In the late afternoon, Brown was standing near the runway when an airplane was rolled out from a hangar. He had never seen anything like it. Not so much the shape, but the construction. No propeller, and an extraordinary sound, a high whining noise, rising in pitch, unlike any engine he had ever heard. The pilot was P. Sayer, Jerry Sayer, Gloucester's chief test pilot. Sayer taxied the E-2839 to the end of the runway. He held the brakes and ran the engine to full power. The whine became a scream. He released the brakes. The aircraft accelerated, and in about 600 yards, it left the ground. Brown watched astonishment. An airplane with no propeller, making a sound that belonged to no category he understood, climbing into the Lincolnshire sky. He had no idea what he was witnessing. He only knew it was something he had never seen before. Pat Johnson, the same Pat Johnson who had helped Whittle draft his patent 11 years earlier at Wittering, slapped Whittle on the back. "Frank, it flies." Whittle's response came out of the tension of the moment. 13 years of rejection, dismissal, financial starvation, and official indifference compressed into a single sentence. That was bloody well what it was designed to do, isn't it? Jerry Sayer landed. The aircraft was immediately surrounded by people rushing from every direction. The secret was still a secret officially, but you could not hide that sound. People in the surrounding area had heard something they could not explain. One officer was said to have asked another, "How does that thing work, John?" And John replied, "Oh, it's easy, old boy. It just sucks itself along like a hoover." Another eyewitness claimed there was a Merlin engine hidden inside the hollow fuselage with a little propeller he had personally seen. He was a reliable witness, he claimed. Eric Brown gravitated toward the officers' mess, where a group of men were in a state of barely contained hilarity. He asked what had happened. Still no one would say. But he could tell something quite momentous had occurred. The flight vindicated Frank Whittle, and when the Air Ministry authorized a test at 17,000 feet, the E-2839 delivered a verdict that silenced even the skeptics. At that altitude and engine speed, the little experimental plane reached 375 miles per hour. It was faster than the Spitfire. The news reached London. It reached Winston Churchill. The Prime Minister's response was immediate. He ordered 1,000 Whittle engines, but the E-28/39 was not a warplane. It could not carry guns. It could not fight. The plane that could fight the Gloucester Meteor, code-named F-940, the twin-engine jet fighter that would become Britain's answer to the Luftwaffe, was still on the stocks, and its production was about to become a disaster. The Air Ministry did not give the job of building the Meteor's engines to power jets. The company that had invented the turbojet, that had built and tested it, that understood every tolerance and every failure mode, was passed over. Instead, the contract went to Rover, a car manufacturer. Rover had no experience building aircraft engines. They had no background in gas turbine technology. They had never dealt with the temperatures, pressures, and rotational speeds that a jet engine demanded. But they had factories, and they had capacity, and the ministry needed engines built in volume. The result was catastrophe. Rover could not build the engine. They did not have the people who could do the job. Their engineers attempted to redesign components they did not understand. Changes were made to Whittle's specifications without consultation, without testing, without any grasp of why those specifications existed in the first place. The Meteor, the jet fighter that could have given Britain an uncatchable advantage in the air, was delayed, not by weeks, not by months, by 2 full years. And then something worse happened. Whittle had intended that Rover would be a subcontractor working under Power Jet's direction, building to Power Jet's designs. But Rover went behind his back. They approached the Air Ministry directly and lobbied for their own contracts, independent of Jet's, outside Whittle's control. The ministry agreed overnight. The company that was supposed to be building Whittle's engine under his supervision became his competitor, a competitor that possessed every piece of technical information Whittle had ever produced because the ministry had ordered Power Jets to hand it all over. Whittle was a serving officer. He could not refuse. He could not sue. He could not take his patents and walk away. National considerations came before commercial considerations. He had to accept that his own government had taken his life's work and given it to people who were failing with it, and he could do nothing. The war did not wait. While Rover fumbled with the Meteor's engines, Germany's jet program was advancing. The He-178 had not entered production. The Nazis had never liked Heinkel, and they cancelled his promising jet fighter, the He-280, despite its potential. But at Messerschmitt, the Me-262 was taking shape, a twin-engine jet fighter, faster than anything in the Allied arsenal. A machine that would terrify every bomber crew that encountered it. If the Meteor had been ready in 1942, as it should have been, as it would have been without Rover, Britain would have had a jet fighter in the sky before Germany. The technological advantage would have been entirely on the Allied side. Instead, by the time the Meteor finally entered service, the Me-262 was already flying combat missions. In the middle of this debacle, the British government made another decision about Whittle's engine, one that would have consequences far beyond the war. In 1941, Great Britain shared the jet engine with the United States. The Americans had been told about Whittle's invention earlier that year. Their own top scientists had already considered the concept and dismissed it. The gas turbine engine, they concluded, could hardly be considered a feasible application to airplanes. The finest technical minds in America had looked at what Whittle had built and said no. The British government expected to keep the rights to Whittle's invention. They did not intend to give their technology away to a future industrial competitor. But that is exactly what happened. The engine was shipped across the Atlantic in pieces, packed into the bomb bay of a consolidated Liberator. The Power Jets team that accompanied it spent the flight in quiet terror, convinced that the pilot might pull the wrong lever and drop them all into the ocean. On the night of October the 4th, 1941, The engine arrived at a Boston airport under conditions of extreme secrecy. The company selected to build it was General Electric, a firm with vast resources, enormous manufacturing capacity, and the engineering depth to reverse engineer a turbojet in a fraction of the time it had taken Whittle to develop one. General Electric had their version of Whittle's engine running on a test stand by April of 1942, less than 6 months. And 6 months after that, the Bell Aircraft Company had a twin-engine jet flying. Whittle went to America himself at the end of May 1942 to assist. The Air Ministry insisted he travel under an assumed name. He called himself Whittle. There were times, he admitted, when he forgot the name. He would sign hotel registers ordering early morning coffee, half asleep, and write his real name. Whittle instead of Whittle. He was told it didn't matter. The waiter was an FBI agent. In America, Whittle saw something that wounded him more deeply than any rejection from the Air Ministry. He saw enthusiasm, resources, speed, cooperation. General Electric had embraced the jet engine with a commitment that made the British effort look like an afterthought. It was most satisfying, he said, to see the work GE were doing. They got on with the job so fast. It was remarkable. Their enthusiasm was most inspiring. And then the sentence that carried the weight of a decade. I thought at the time if only I had had kind of cooperation a few years earlier. What a difference it would have made. Back in Britain, the rover disaster finally reached its breaking point. In December of 1942, a solution was found. Rolls-Royce, the most prestigious aero-engine company in Britain, took over the production of Whittle's engines. The man who made it happen was Ernest Hives. He was the chief executive of Rolls-Royce, and he had come to a conclusion that the rest of British industry was still resisting. The jet engine was the future, and Rolls-Royce was not going to be left out. Hives was a pragmatist. He had none of the idealism that drove Whittle, and none of the incompetence that had crippled Rover. He was a man who saw power and moved toward it with the directness of a locomotive. Whittle understood him completely. I would call him an honest rogue, Whittle said later, because when he was going to do the dirty, he told you in advance. And one of the things Hives said to Whittle directly, without evasion, without apology, was this: we are going to be at the center of this job, and nothing you can do will stop us. It was not a threat. It was a statement of fact. Rolls-Royce had the factories. Rolls-Royce had the workforce. Rolls-Royce had the relationship with the ministry. And Rolls-Royce intended to own the jet engine, not as a partner of power jets, but as its replacement. Whittle recognized the honesty. He also recognized the danger. But in December 1942, the priority was not corporate politics. The priority was getting the Meteor into the sky. And Rolls-Royce could do what Rover could not. With Rolls-Royce behind it, the engine program accelerated. The Meteor made its first flight, 1943, 2 years later than it should have been, but finally airborne. Britain had a jet fighter, yet Whittle could not escape the arithmetic. If the Air Ministry had pursued his idea in 1929, when he first offered it, a jet fighter could have been ready by the start of the war. Instead, the Meteor arrived in July of 1944, assigned to 616 Squadron at Manston in Kent. And its first mission was not to fight the Luftwaffe's fighters. The Luftwaffe could no longer mount air raids over Britain. The Meteor's first job was to chase down a weapon that had no pilot at all. The V-1, Germany's flying bomb, a cruise missile powered by a pulse jet engine, launched from the coast of France, aimed at London. It carried nearly a ton of explosives and traveled at 400 miles per hour, just fast enough to outrun most piston engine fighters. The Meteor could catch it. Over the skies of Kent, Meteor pilots from 616th Squadron intercepted V-1s heading for the capital. Some shot them down. Some, when their guns jammed, used their wingtips to flip the missile's gyroscope. sending the bombs spiraling into the ground in open countryside instead of falling. Land's work, important work, but it was not the work the meteor had been designed to do. It had been designed to fight enemy aircraft, and by the time it was ready, the enemy aircraft it was meant to fight, the EE-262, was already operational on the other side of the channel. The RF deliberately kept the meteor away from the European continent. The fear was simple and justified. If a meteor was shot down over German territory, the enemy would recover the wreckage and gain access to British jet technology. The advantage, already eroded by years of delay, would be gone entirely. The war would end before the meteor ever fought the Me-262. In January 1944, the British and American governments jointly announced the existence of the jet engine to the public. The reasons for lifting the secrecy were never entirely clear to Whittle, but the effect was immediate. "It was like the world blew up around me," he said. His son David remembered it, the shock of it. The family had been living in complete secrecy. David knew his father was doing something important only because his mother said so. "Oh well, Daddy is doing something very hush-hush." And then one morning, the house was surrounded by reporters. The newspapers carried Frank Whittle's face on the front page. The Daily Herald quoted Dorothy, "I knew Frank had a secret." Overnight, the man who had been dismissed, underfunded, and systematically undermined became a national hero. The public saw the triumph, the brilliant engineer, the revolutionary engine, the jet fighter defending London. They did not see what it had cost or what was about to happen next. In the summer of 1944, Frank Whittle appeared to be at the peak of his life. He was a national hero. His face was in every newspaper. His name was spoken in Parliament. The engine he had invented was powering a jet fighter that defended London against Hitler's flying bombs. The public adored him, the working-class genius from Coventry who had given Britain a wonder weapon. Behind the headlines, the reality was already crumbling. Power Jets had grown. It now had a custom-built factory, a proper facility, not a converted foundry, and a team capable of producing engines in batches of 40 or 50. Whittle had built what he had always wanted, a first-class nucleus for a proper manufacturing organization. And he had plans that went far beyond the meteor. 2 projects were in progress at Power Jets. Both would have changed the course of aviation history. The first was the LR-1, Long Range 1, a turbofan engine. Whittle had been bothered from the earliest days of the turbojet by what he saw as its fundamental weakness: propulsive efficiency. A turbojet wastes energy. The exhaust gas leaves the engine at tremendous speed, far more speed than is actually needed to push the airplane forward. That excess velocity is wasted thrust, lost energy, about 50% efficiency, compared to 80% for a propeller at moderate speeds. The answer, Whittle believed, was to gear down the jet, add a fan to the front of the engine, use it to move a large volume of air around the core, bypassing the combustion chamber entirely. This cold bypass air would create additional thrust at lower velocity, more efficient, less fuel, longer range. He had taken out a patent for this concept in 1936, 10 years before any other turbofan existed. If the LR-1 had been built, it would have been the first bypass engine in the world. Whittle envisioned it powering long-range bombers for the Pacific War. He envisioned it in transatlantic airliners. He was describing, in 1943, the exact engine that would eventually power every commercial aircraft on Earth. The second project was the engine for the Miles M52 Britain's supersonic airplane, an augmented jet with afterburning designed to push a small experimental aircraft to 1,000 miles per hour, faster than sound. Both projects were real, both were funded, both were technically advanced, and both were living on borrowed time. In 1944, the British government looked at Power Jets and saw a problem. The company was privately owned, but its founder was a serving RAF officer and its funding came from public money. The arrangement was messy. The contracts were confused. No effective agreements governed the relationship between power jets and the large engine companies that were now building Whittle's designs under license. Whittle himself had proposed a solution. He suggested that the entire turbojet industry should be nationalized, all the companies brought together into a single government establishment, with power jets at the top of the pyramid and Whittle as chief engineer. It was a reasonable proposal from a man who had spent 14 years watching companies either reject his work or steal it. Stafford Cripps, the Minister of Aircraft Production, heard the proposal, and then he used it against the man who made it. Cripps nationalized power jets. Only power jets. None of the other companies were touched. Rolls-Royce kept its independence. De Havilland kept its independence. Every major engine firm was left untouched. The large companies, the ones that had rejected Whittle's idea for a decade, and then demanded access to his technology as a wartime necessity, were not affected. Only the company that had pioneered the entire technology from nothing was taken. The large engine companies had lobbied against nationalization, but only against their own nationalization. They were perfectly happy to see power jets absorbed into a government body. They told the ministry they were not going to have the government competing with private enterprise. And the minister, the same minister who had used Whittle's own proposal as the instrument, caved in. Power jets was merged into the National Gas Turbine Establishment. The people who had invented the jet engine, who had built it in a rented factory with no money, who had proven it against every prediction, were stripped of the right to design and build engines. We, the people who had pioneered the whole thing, Whittle said, were deprived of the right to design and build engines. He resigned. Most of his leading team members resigned with him. The damage did not stop there. In February 1946, the new Labour government cancelled both projects that power jets had left behind. The LR1 turbofan, the first bypass engine in the world, patented a decade before anyone else conceived of such a thing, was scrapped. The engine for the Miles M52 supersonic airplane was scrapped. Both technically viable, both years ahead of any competitor, both killed by administrative decision. And the justification offered for cancelling the supersonic program was a sentence so staggering in its wrongness that it deserves to be repeated without commentary. The minister said that people would not want to fly at speeds more than about 250 miles per hour, 250, when the Meteor was already flying at 480, when the Me-262 had exceeded 540. When Whittle's own M52 engine was designed for 1,000. 25 years later, Concorde would cross the Atlantic at 1,350 miles per hour, and Frank Whittle, the man who had foreseen supersonic flight before the war ended, would sit in its cabin as a paying passenger. After the German surrender in May 1945, Allied teams swept through the Reich's abandoned factories and airfields, cataloguing what they found. Eric Brown, the same naval pilot who had watched the E-28 take off at Cranwell in 1941 without knowing what it was now commanding officer of the captured enemy aircraft flight at Farnborough. He was sent to Germany to examine advanced aircraft and to interrogate their designers and test pilots. Among them was Hans von Ohain. Brown sat across from the young German physicist and asked the question that had haunted the British jet program from the beginning. What was von Ohain's connection to the Whittle patent? The patent that had expired in 1935. The patent whose technical details had become public record. Had von Ohain read it? Had his work been influenced by it? Was Germany's jet engine a parallel invention, or had one genius unknowingly shown the other the way? Von Ohain did not answer. He was, Brown said, very non-committal. He sidestepped the question as much as he could. The question was never conclusively resolved. Brown flew the captured German jets, including the Me-262. He found its Jumo 4 engine to be more aerodynamically sophisticated than Whittle's centrifugal design. It used an axial flow compressor, which was theoretically more efficient. But in practice, it was desperately unreliable. The Jumo 4 had a service life of just 5 hours before it had to be scrapped, and it was dangerously sensitive to throttle movements. Any sudden change in power, acceleration, or deceleration could cause a flameout. Brown found it difficult and unforgiving to operate. Whittle's engines were heavier, less aerodynamically elegant, and far more reliable. The genius engineer had not built the most advanced jet engine in the world. He had built the one that worked. The years after the war were cruel to Frank Whittle. He managed to remain in the RAF. He was promoted to Air Commodore in 1946, a rank that recognized his contribution and gave him standing in a service that had been everything to him since he was 15 years old. But his health was broken. The years of overwork, the nervous exhaustion, the unrelenting stress of building the future while fighting the system that was supposed to support him, all of it had accumulated into a debt that the body eventually collects. In 1948, he was declared unfit for flying. For a man who had dreamed of flight since the age of 4, who had built a tin Blériot monoplane as a toy, who had crashed 3 airplanes at Cranwell out of sheer exuberance, who had thrilled crowds at Hendon with crazy flying, being told he could no longer fly was the last straw. He and the RF agreed that he should retire. Very sad, his son David said later. Very sad. The Air Force was everything to him. The public saw none of this. What the public saw was a war hero collecting his rewards. In 1948, Whittle went to Buckingham Palace and received a knighthood, Knight Commander of the Order of the British Empire. Sir Frank Whittle. He also received a financial award from the Royal Commission on Awards to Inventors. £100,000. £100,000 for the jet engine, for the invention that would power every military aircraft, every commercial airliner, every cargo plane on Earth, for the technology that would shrink the world, that would make global travel possible for ordinary people, that would generate hundreds of billions in revenue, for the companies that built the engines and the airlines that used them. The amount many people felt was not remotely adequate. And then the final indignity. No engine company hired Frank Whittle. The man who had founded the jet engine industry could not find a job in it. Rolls-Royce did not want him. They had his technology, and they did not need the man who came with it. He was too important to employ, too famous to manage, too much of a reminder that the entire industry was built on the work of a man it had rejected, exploited, and discarded. In many ways, Whittle said, I paid quite heavily for the work I did. There was the awful race against time that dominated life. On top of the technical difficulties, there were the financial difficulties. There was the skullduggery of people who were messing things up, frustration after frustration, and it took its toll. I began to have a series of nervous breakdowns, and it was years before I really recovered my health. Dorothy had watched all of it, the refusals, the sleepless nights, the breakdowns, the nationalization. She had held the family together, while her husband held the engine together, and neither task had been possible without cost. David remembered her words. How can they treat him like this, she would say. How can they treat him like this? The jet age took off without Frank Whittle. Britain launched the world's first jet airliner, the de Havilland Comet. Beautiful, elegant, 4 turbojet engines, the fulfillment of everything Whittle had imagined. He joined WWII as a consultant to help introduce the Comet into service, and immediately raised a concern that no one wanted to hear. He was worried about the windows, the square windows. He wrote about it in his diary in 1949. He was concerned about the strength of the square window design. He made suggestions to de Havilland for how the problem could be addressed. His advice was ignored. When the comets began to crash, breaking apart in mid-flight, killing everyone aboard, the investigations found that metal fatigue around the square window frames was a primary cause. The genius engineer had seen the danger, and once again no one had listened. The world moved on. Boeing built the 707. Pan Am ordered it. The American aircraft industry, energized by the jet technology that Britain had given them in the Bombay of a Liberator in 1941, captured the global market for commercial aviation. By 1960, the airlines were buying American, and in 1960, the bypass engine entered service, the turbofan, the exact technology that Whittle had patented in 1936 and built a prototype of before the government cancelled it. The turbofan transformed commercial aviation, better fuel economy, longer range, lower noise. It was just what the airlines needed. It was what Whittle had designed 15 years before anyone else. The ultimate vindication and the ultimate reminder of what the cancellation had cost. In 1976, Frank Whittle left England. He moved to the United States. He became a research professor at the United States Naval Academy in Annapolis, Maryland, the country that had embraced his engine in 1941, that had built it in 6 months when Britain had starved him for a decade. That country welcomed him when his own no longer seemed to know what to do with him. He felt more recognized over in the States than he did over here, his son David said. The Americans were very good at slapping him on the back and telling him what a good chap he was. And in America, something extraordinary happened. Something that no novelist would dare to invent, because it would seem too neat, too symmetrical, too perfectly constructed to be true. Hans von Ohain was there. After the war, the German physicist had moved to the United States to work on jet propulsion research for the U.S. Air Force. He had settled in Dayton, Ohio, Wright-Patterson Air Force Base, the same base for the Wright brothers, who had started powered flight in the first place. Two men who had invented the same engine on opposite sides of a world war, who had raced each other without knowing the other existed, who had been separated by language, nationality, ideology, and 6 years of the most destructive conflict in human history, met on American soil. They were fascinated by each other's work. They compared notes. They discussed the technical choices each had made: Whittle's centrifugal compressor versus von Ohain's axial flow, the combustion solutions, the turbine metallurgy. They talked about the years of struggle and the different forms that struggle had taken. Whittle's battle with his own government, von Ohain's work within a regime that was collapsing around him. They became close friends. The genius engineer from Coventry and the genius physicist from Dessau, enemies by circumstance, brothers by obsession, spent their final years in the same country, bound by the only thing that had ever truly mattered to either of them: the engine. In 1986, the recognition finally came. The Queen awarded Frank Whittle the Order of Merit, one of the highest honors in British public life, limited to 24 living members. From the early 1980s onward, people began to remember who had pioneered the turbojet. The country that had dismissed him, underfunded him, nationalized his company, and cancelled his projects, finally turned around and said, "We remember. We know what you did." It was late, but it was not nothing. Frank Whittle spent his final years in America. Still thinking about engines, he took an active interest in Concorde. He advocated publicly and privately for a second generation of supersonic transports, faster, larger, capable of carrying 300 passengers at Mach 2.3, 2,000 miles per hour. San Francisco to Tokyo. He was still seeing the future, still pushing the boundary, still frustrated that the world moved so slowly toward what he already knew was possible. His son Ian had become a captain with Cathaps flying Boeing 747s on long-haul routes across the Pacific. The son of the man who invented the jet engine was flying jets for a living. The circle was complete in a way that Whittle could never have predicted when he was filing his patent at the age of 22. One day, Whittle flew with Ian in the cockpit, a passenger in the jump seat of a 747, watching his own son command a machine that existed because of what he had built in a rented factory in Rugby with £2,000 and a 1 in 30 chance. They were approaching Hong Kong, Kai Tak Airport, the most famous approach in commercial aviation, a steep, curving descent between mountains, a hard right turn at 1,000 feet, buildings and hillsides filling the windscreen, and then the runway appearing at the last possible moment. Ian had not briefed his father. Whittle sat in the cockpit and watched as the 747 descended toward what appeared to be a mountain. At 1,000 feet, the aircraft banked hard right. The hills were close enough to touch. The runway swung into view. Ian flew the approach with the calm precision of a man who had done it hundreds of times. Frank Whittle, the man who had wrecked 3 airplanes at Cranwell, who had performed crazy flying at Hendon, who had stood 3 feet from an engine running out of control and not moved, was white-knuckled, his hands gripping the seat, his face pale. His son was flying an airplane at 1,000 feet toward a mountainside, and the genius engineer who had made the whole thing possible was terrified. They landed safely. Ian looked at his father and understood. There is a difference between the man who invents flight and the man who lives inside it every day. Sir Frank Whittle died on the 9th of August, 1996. He was 89 years old. On the last morning of his life, his son Ian leaned over the bed and said, "Dad, let's put on our kit and go flying." Frank Whittle opened his eyes. He looked at his son, and he smiled. That evening, with his second wife Hazel holding his hand, he died. Ian stood alone afterward, and wondered. He wondered if his father went flying, and if he did, if he went on his own, or if he had a companion. Whittle was cremated in the United States. The British air attaché brought his ashes home across the Atlantic, the same ocean that a liberator had once crossed with a jet engine in its bomb bay. Ian met the airplane at Heathrow. He brought the ashes home and placed them on the bookshelf in his study, next to the ashes of his mother Dorothy, who had died just 3 weeks earlier. The woman who had asked how can they treat him like this, and the man she had loved through all of it, side by side on a shelf. Together again after everything. Ian decided to enter them at the church at Cranwell. The RF organized the ceremony. A Gloucester Meteor and a de Havilland Vampire, the first generation of British jet fighters, both powered by engines that Frank Whittle had designed, flew overhead as the ashes were laid to rest. A small English church in the Lincolnshire countryside. The last resting place of a man who did not just change the face of the earth, he enabled us to see what it actually looked like. He had arrived at Cranwell as a boy who was too short. He had left it as the man who saw the future. And now he had come back carried home by the machines he had made possible, to the place where a thesis scored 30 out of 30, and a genius engineer first imagined an engine with no propeller, no pistons, and 1 moving part. Today, 1.5 billion passenger journeys are made by air every year, cheaply, safely, across oceans and continents, in aircraft powered by turbofan engines, the exact technology Frank Whittle patented in 1936 and saw cancelled before it could change the world on his terms. Every one of those flights is a vindication. And every one is a reminder of how long the world made him wait.